Okay, so let's talk about operational amplifiers. To understand how an operational amplifier works, you need to understand how transistors and diode work. But you do not need to understand how transistor and diode works to be able to use an operational amplifier. In basic electronic circuit theory, we'll be trying to understand how to use an operational amplifier. And the first question we want to ask is, what is an operational amplifier? Basically, an operational amplifier is a voltage controlled voltage dependent source. A voltage controlled voltage dependent source. It can also be used as a voltage or current controlled current dependent source. We can use it to perform mathematical operations like addition, subtraction, scaling, integration, and differentiation. What the operational amplifier does in essence is that it amplifies the difference between the signal supplied through the non-inverting input and the signal supplied through the inverting input by some multiple. An operational amplifier has different parts, you see. We have two inputs, which are the non-inverting input and the inverting input. We have one output, and we have the positive power supply and the negative power supply. Now, let us label the voltages in our op amps. If we call the voltage through the voltage across the non-inverting input VP, we can call that at the inverting input VN. At the output, we can call that V0, and here we have V positive, V negative. So what we are saying in essence is that V0, that is the output, is equals to the difference between these two, that is Vp minus Vn multiplied by some number. But here's the thing. One major characteristic of an ideal amplifier is that this A is infinite. The gain is infinite. Although in practical amplifiers, A is just very large. A is very large in practical amplifiers. But in an ideal amplifier, A is infinite. For this reason, V0 tends to go to infinity. But here's the thing, in an operational amplifier, there are upper and lower limits. So the output voltage in an operational amplifier cannot be greater than V plus or V minus. In essence, the actual function for the output voltage of an operational amplifier would be V0 equals we have three possible outputs: A into Vp minus Vn. We have V plus, we have V minus. Now, we have this V plus in the case where A into Vp minus Vn is greater than V plus. And in a situation where A into Vp minus Vn is less than V minus, that is when V0 is equals to V minus. But when it is in between these two conditions, when the output is in between these two numbers, then the output takes the value of A into Vp minus Vn. Now, this is a graph that explains the behavior of the output voltage of an operational amplifier. And you see we have this line here that symbolizes the linear region. That is where the output voltage of the amplifier is directly proportional to the inputs and the difference between the inputs and the output of the amplifier. Then we have the positive saturation region, and in this positive saturation region, once A multiplied by Vp minus Vn is greater than VCC, it goes into positive saturation, and in the negative saturation region, once it is less than it, it goes into negative saturation. Now, the goal when operating an amplifier most of the time is to keep it in this linear region. And in order to keep it in this linear region, we have to establish certain constraints. And the first constraint, the constraint that we establish in order to keep it in the linear region, since A is infinite, is that we make sure we assume at all times that Vp is equals to Vn. Now that is in an ideal amplifier, in an ideal operational amplifier. But in the case of a practical operational amplifier, the values between Vp minus Vn are not much far apart. They are very, very close because the gain is large, but it is not infinite. Now we know that if we want to keep an operational amplifier operating in the linear region, we need to make sure Vp is equals to Vn, right? But that is easier said than done, because when you put it in a circuit, the values of Vp and Vn will be dynamic. They will change from time to time. They might not be equal from time to time. So the question is, how do you maintain Vp equals Vn? And the way to do that would be to supply a negative feedback to the input from the output. So you send a portion of the output back into the input to correct any changes to the values of Vp and Vn, and to maintain this condition. Now that we're done talking about the constraints on the voltages in an operational amplifier, we should talk about the constraints on the currents in the operational amplifier. Another important characteristic of an operational amplifier is that the input resistance, input impedance equals infinity, and then the output impedance equals 0. Now, if the input impedance is infinite, that means that first off, we know that Vp is equals to Vn, and the input impedance here is infinite. The input impedance here is infinite. That means that Ip will be equals to In, since Vp over R is equals to Ip, and same goes for In. And since the input impedance is infinite, that means that that will be equals to 0. So the input current is 0. The input current at the non-inverting input is 0. The input current at the inverting input is also 0, and they are equal to one another. Establishing these two constraints will allow us to be able to solve any questions on operational amplifier circuits and design circuits containing operational amplifiers.